inori, inori.
Inori. Okay, that's a brutal score. Inori. Hello, your ears can deceive you. What? Listen to these two notes. You can clearly hear the difference, right? Now, what about these two? Not so easy, is it? Even though the difference of 100 Hz stays the same, human hearing is non-linear. They sound practically identical when it's a higher note. And if you're trying to learn Japanese, this flaw is the exact reason why you might struggle to correct your own accent. Today, we're going to visualize the hidden melody of Japanese using sound data, MEL spectrograms, and an AI I built from scratch to grade your accent. Let's dive in. To understand the data, we first need to know what we're looking for. Japanese has 4 main pitch patterns: heiban, atamadaka, nakadaka, and odaka. The most common one, also referred to as flat, is heiban. The first moira, which is just the Japanese word for a beat or syllable, starts low and the rest stays high, like in the word for bridge.
ご覧橋だ
The other 3 patterns drop the pitch at different points. Atamadaka drops immediately after the first beat,
毎日
and nakadaka drops in the middle, like tamago. And odaka stays high until the very end, dropping right when you add a grammar particle like ga.
川が
If you mix these up, I'm sure from context people will still understand you, but to truly improve, a constant feedback loop is important. To actually see what's happening and fix those mistakes, we need to stop guessing and start looking at the physics of sound. If you open up a standard audio file, you usually see a waveform, and this is great for seeing volume, but it's completely useless for seeing pitch. Instead, linguists use a tool in Pratt to generate pitch contours and something called a MEL spectrogram. A spectrogram is basically a 3D map of sound. Time moves from left to right, the frequency or pitch goes from bottom to top, and the brightest of the colors tells us how loud that specific frequency is. But notice the word MEL in MEL spectrogram? Remember the hearing test we did at the very beginning of the video? Our ears are bad at hearing pitch differences at higher frequencies. The MEL scale is a mathematical trick that stretches and squashes the sound data so the visual map perfectly matches how your ear actually perceives and understands sound. This exact visual data is what I use to train my machine learning model using 900 audio samples from the online Japanese accent dictionary. When we look at a native speaker saying a Japanese word on a MEL spectrogram, we see a fluid curving model and the drops in the right places. But when no, I'm kidding. But when we overlay someone like me who's still working on their Japanese pronunciation, the problem becomes obvious. English speakers use stress and we make words louder and longer to emphasize them. Record, suspect. Since Japanese only uses pitch, the disconnect between how we think we sound and how we actually sound is something I found interesting. So, for the last few months, I started working on an AI model that would take your inputs compared to a native speaker and spit out whether the pitch pattern was the same, and also display the pitch graphs to help you with visual feedback. How, you may ask? How did you manage to do something? Imagine you have 2 twins who also just happen to have the exact same brain. You give person A a picture of a dog, and then you give person B another picture of a dog, and you ask them both independently, what animal is this? The answer, of course, should be a dog, right? Now, imagine you also give them a box and ask them to place the boxes depending on how close the 2 pictures are in terms of dogness. Some dogs are very similar and others are not even a dog at this point. Sorry. This is basically what my model does. It uses twin brains to compare both audios and then rates how similar they are in terms of pitch. Since this is a beta version, the math for the final step still needs tweaking because if the pitch is slightly wrong, it rates them too far apart, hence the scores from 0 to 1%. And this is basically how a Siamese neural network works. Sounds scary, right? Since this model only compares pitch patterns and doesn't check if you're saying the correct word, I first fed the audio into Google speech recognition, and anything above a 60% match is considered valid, of course to account for small errors. Now, why is there another scoring system though? Good question. This is how much the graphs touch. It mathematically stretches both audio so the syllables align perfectly, regardless of speed, and returns a score. More importantly, it stops AI from decimating your score to crazy numbers. And that brings us to the combined score. This is the pitch pattern accuracy weighted 40% and the alignment score weighted 60%, all added together. Language learning is hard, and pitch accent is the one thing most learners completely ignore until it's too late. And now you can actually see and test it. I've made my AI tool completely free and public, and I want to see how good your pitch actually is. Go to the link in the description right now and record yourself saying a few test words and see if you can beat my score. Let me know what score the AI gives you in the comments below. I will be continuously updating the model to make it better and more forgiving, but for now it is pretty strict.
組み込む
I loved learning and researching about this topic, and if you're a massive nerd like me and want to see the Python code and machine learning architecture behind this, smash that subscribe button! And I'll be doing a deep dive follow-up on how it was all built. Thank you for watching, and now go get your score.